can't win. So, yes, the purpose of this is to demonstrate that Evan is stronger than Blake. What I have here is a 1 kilogram mass, and Evan, I'd like for you to show everybody how easy it is if you hold this. Just grab the meter stick and then support the 1 kilogram mass. See? Easy, easy, easy. All right, Blake, you grab the meter stick, and I'd like for you to demonstrate how easy it is to hold the 1 kilogram mass. Oh, you're trembling there, Blake.
Blake,
how you doing? This is pretty hard. He's doing okay. He's doing okay. He's giving a hand, guys. He's doing really well. Blake, but I think we all agree that Blake is having to work a lot harder than Evan was to hold this up. All right? Thank you. Can anybody tell us why? Is it the opposite end? Somebody said something about leverage, yeah? Something about torque. That's exactly right. So what we're going to be talking about today is torque. We'll call it a draw. Evan is at least the strongest Blake. So we'll be talking about torque here, which is related to this concept of leverage. And it's actually related to several different simple machines that are used to decrease the amount of force that it takes to get a job done. So, let's see how far we can get. A little bit of review of rotation so far. We have talked about two items with regard to rotation. One is strictly how the angles change. And those are governed. Those are governed height. The angles are governed by the equations of motion. In the rotational sense. And we discovered on the exam that some of you needed to make sure that you memorize these and had these at your disposal. We also talked about the relationship between rotation and linear speed, or linear motion. And that is that if I have an object on the edge of a circle of radius r, and that object is traveling around, then the distance that the object travels is the radius times the angle that the object travels. And the speed of that object is the radius times the angular speed. And the tangential component of acceleration is the radius times the angular acceleration. And so this allows us to go back and forth between angular quantities and the linear quantities here. We also remembered that centripetal acceleration is the same thing as v squared over r, so that when I substitute r omega here and simplify algebraically, then I get an expression in terms of omega as r omega squared. And this is what we've done so far with regard to rotation. What we want to talk about today is, why does rotation happen at all? Yes?
What's the OA?
Acceleration.
It's an A. It's not an
Oh, you're talking about here?
Yeah.
Yeah, that's a sub t. The tangential component of acceleration.
So are you like gonna go over this is what we're doing the whole day, right? Like rotation. Oh, like this kind of. I'm just like this. Like I totally just missed it. Well, I didn't miss it, but I just totally did not pick up on this when we learned it first. Like I didn't understand the concept.
Okay. Well, I can take a few minutes to talk about it. I don't want to miss too much of today's lesson here. What specific questions do you have?
Well, can you? Okay, so like. Can you explain what the variable means?
Omega.
Sure. Theta is going to represent the angle, measured usually from due east, and with a positive counterclockwise orientation. Omega is the angular speed. It is the rate of change of angle. so that an average omega will be your change in angle over your change in time. So you want to think about that as how quickly we are turning around. And then alpha is the angular acceleration, which is the rate at which my angular speed is changing. And alpha and omega have the same relationship to each other as velocity and acceleration do. So that if an object is speeding up, then alpha and omega have the same sign. And if an object is slowing down in a rotational sense, then they have opposite signs. Does that help? Is that what you were asking?
Yes.
Okay, good.
Along the lines of searching, like if people are given a problem, how do you like figure out what I have?
Okay. Why don't you find an example
Just like I
of
feel
that?
like problem number 1 is really easy, but it's like I just
Okay, go ahead and look that up for us. Deja, did you have excuse me, did you have questions?
Oh, no, everything. Yeah.
Okay, good. Good. Other questions? Did you find it? Go ahead.
Carries uniformly from rest to 50,000 RPM and 226.
Hang on a
How
second.
many revolutions did it turn in this
Wait. Uniformly from rest to how many revolutions per minute?
15,000.
15,000. In how many seconds?
220.
And then the question is,
How many revolutions did it turn in this?
okay. So first of all, visualize this. Have you guys used centrifuges in the chemistry lab? Do you know what they are?
We didn't need pink on it.
Okay. All right, yeah. So how many of you can picture a centrifuge of some sort or another? Some of you. All right. Well, for the rest of you, the centrifuge is basically just a small thing here that spins really fast. And you put glass or plastic tubes in it called cuvettes. And as it spins around, then all of the solids that are in the cuvette get pushed to the outside. And so it's a great way to filter out solids out of some kind of liquid suspension that they're in. So in chemistry, generally speaking, if we create a solid in a test tube and we want to extract that solid, we'll simply put it in the centrifuge, spin it up, and there it is. Yes?
So why does the solid comes out instead of the liquid is solid? And so if you spin it, wouldn't let everything just come straight out?
Think of it as density. The solid is more dense than the liquid.
Yes.
And so the tube itself is closed when you put it in there. And so when you spin it around, it essentially creates artificial gravity to the outside, and the heavier stuff goes down in the artificial gravity. Okay, so let's identify here. First of all, from rest, what is that telling us?
Zero.
What is zero though? How do I label it? Initial velocity. In an angular sense, the label for initial velocity is angular speed omega. 2, here. What is this giving us? Well, we can let our units be our guide. RPM stands for revolutions per minute, which is an angular speed. So we're going to say that omega final is equal to 15,000 revolutions per minute.
Oh wait, why wouldn't it be the little half, the omega, the half little infinity sign thing?
Why would
The
it be?
Jesus fish.
Yeah.
That thing.
Because this is an angular acceleration.
Wait, what's this?
This is an angular speed.
Oh, I thought revolutions per minute would be an exo. Oh, it'd be revolutions per minute per minute.
Yeah,
Okay.
there you go, right. So this would be in revolutions, not revelations, C per second squared, or radians per second squared, or something per time squared, because it is the rate of change at the rate of change of the angle. And of course, the 220 seconds is the amount of time that it takes. And now they're asking for how many revolutions did it turn, and revolutions is measuring actual angular displacement here, the delta theta. It's measured in revolutions. So. And so this is what we're trying to define. One thing that is confusing about the rotational stuff is simply that we have 3 different sets of units for measuring angles: degrees, radians, and revolutions. And so sometimes when you look at the problem, you may forget to convert the units or something like that. And then you get an answer, and you look back at the book, and it's not the same number. And so you think I did it wrong. Until you realize, oh, I got 1 revolution, they wanted 2 pi radians. So before you declare yourself wrong, just check the units and make sure. Okay?
And how do you convert into them?
Well, keep in mind what 1 full circle is. 1 full circle is a complete revolution. It is also 360 degrees, and it is also 2 pi radians.
Okay.
And that gives you your conversion. All right, so I look at this, and I now say I'm trying to find this guy, and I have this given information here, so what can I do with this? Well, it looks like I can figure out alpha from this information right here. And so I say omega equals omega 0 plus alpha t, or we don't have the acceleration, but we can figure it out pretty fast with this. And I look at this and I realize I can find alpha, but it's going to be awkward because I've got minutes on the one hand and seconds on the other, so I probably better convert. Let's do it all in terms of minutes.
Would it work if you did final minus equals 2 over time with the acceleration? Why did this problem not like it, I think?
That's just replicating the algebra we have from solving this. So 220 seconds should be 3 minutes and 2/3, right? 3.67 minutes. Yep. So we'll replace this with 15,000 revolutions per minute equals alpha times 3.67 minutes. And now when we solve for alpha, what we get is 4091 revolutions per minute squared as our alpha. So this information we can now come back and use to solve for delta theta, because we know that delta theta equals omega 0 t plus 1/2 alpha t squared, and 0 for this one, and plug in here, and we're going to get a very large number of revolutions, somewhere in the order of about 20,000, maybe 25,000. 27,500. Did that answer your question about labeling and how all that goes? Did that answer your question about labeling and how all that goes?
Yeah, it helped.
Okay. Yes.
Okay, so like the book and like the online thing, they use this one equation that it's like beta equals 1/2 W0.
Ah, yeah.
And I don't.
Yes,
what
I
is
was
that?
getting there. You may remember that when we talked about the three equations of motion, I said there's a fourth one that's sometimes used. When you have constant acceleration, it turns out that the average velocity is simply the average of the initial and final velocities. Okay? And this is only valid for constant acceleration, but for almost all of our problems, we work with constant acceleration. Well, the analogous thing is true about constant alpha. If we have a constant angular acceleration, then the average angular speed will be equal to the average of initial and final angular speeds. And this allows us to take a wonderful shortcut, because as I know, the average angular speed is delta theta over delta t, right? So if I multiply both sides of the equation by delta t, then I find my delta theta directly, and if I replace it with this right here, now I have a formula that I can use directly for the information that's given in order to find this right here. So we could have shortened our work considerably by doing 15,000 plus 0 over 2 revolutions per minute times our 3.67 minutes, and that comes out to 7,500 revolutions. 75,000 revolutions. Oh, 2750. Thank you. I was wondering why that looked really weird. So this is a shorter solution path, but it required knowing some additional information. That's a great question. Good. Anybody else?
I have a question.
Yeah.
I did chapter 7, so chapter 8 or 9 tonight.
Nice. Did you learn something?
I did learn stuff.
Cool.
Like, should I have to redo chapter 8 again?
You want to know rotational stuff, right?
Yeah.
It's not about getting the check, it's not learning the material. Better? Okay. So today we want to talk about what is it that causes rotation. And I take you all the way back to Newton's second law. Newton's second law was that the sum of forces is equal to mass times acceleration, and the net force equals mass times acceleration. And so we think of forces as that which causes motion, and it causes it by changing your velocity. Well, I want you to imagine for a moment that I've got a kilogram mass on the end of a meter stick, so that I have 10 newtons of force pulling straight down right here. And pretend for just a moment that there is a little pin that's holding this meter stick in place, but no other force acting on it. So as soon as I put this on, as soon as I let go of that, it's going to go just like that. So it's able to swing freely on a hinge or a pivot. Okay. Now, if you take a look at just the motion here, and I'm not going to put the whole 10 newtons on because it would totally kill this. But if you take a look at the motion, you can see what happens. The pivot doesn't move, but the result is that the meter stick now begins to speed up. It goes from 0 to some larger speed. In other words, the force that is applied to the end right here causes an acceleration. That makes sense. Okay. So, let's take this F net equals ma and consider what kind of acceleration is caused by the force here. You remember that the tangential acceleration, which is pulling down, is r times alpha, just like that. That was one of our equations that we had in the previous page, right? Okay. And so now we consider, what kind of effect exactly does this force have? What we saw from the Evan-Blake experiment is that the further out that force is applied, the greater tendency it has to cause rotation. That's our big idea. And some of you called that leverage, and that's exactly right. So the more leverage a force has, the greater tendency it will have to cause rotation. How do we measure that leverage? We're going to measure that leverage as the product of force times distance. We're going to call that torque. Not torque, but torque. Is the tendency or the ability to cause angular acceleration. We're going to use the Greek tau for torque, and we're going to say that that is equal to the product of force times distance. Wait a second. Force times distance we've done before, and that was work. So how is that different from work? Well, it's different in this way. Work was force times distance in the parallel direction. If I have a force like so, and I have a distance like so, then these two are parallel to each other, where work is equal to FD cosine theta. Here, in order to exert torque, the force has to be actually perpendicular to the distance over which it is operating, not parallel to. This kind of force doesn't cause any rotation around this point. This kind of force, one that is perpendicular to the distance of operation, does. So the torque is going to be force times the perpendicular component of distance. Now let me show you how to read this off of a diagram. Go back to our situation right here. Let's say for convenience that this is 1 meter distance. And I see that the distance right here is exactly perpendicular to the force that is being exerted. And I say, aha, the amount of torque that's being exerted in this situation is equal to the force times the perpendicular component of distance, which gives me 10 Newton meters worth of torque. Just like that. Yes?
So, what's the unit of torque? Do you use like joule or you just use like...
That's a really good question. We're going to use Newton meters to distinguish it from the joules that we use for work.
So isn't this technically supposed to be something?
And we're also going to see in a future lesson that there's a relationship between torque and work, but what it's missing is an angle through which you turn. So we're going to use Newton meters. It's really like Newton meters per radian, but the radian is invisible. Now, to get a sense of this, what I'd like for you guys to do is at your tables, I'd like for you to exert some torques on each other in this way. One of you hold out your hand, and the other of you push first straight down on the other person's hand. Right? Can you feel the torque that's being exerted there? All right. Now, same experiment, but this time push with an equal amount of force directly into the hand.
Like this?
Yeah. Now there is no rotation. There's no tendency to rotate. You see the difference? Same force, same distance, but because the angle is different, because it is parallel to the distance rather than perpendicular to it, there's no tendency for rotation. Does that make sense to everybody? Yeah.
I still think distance like the perpendicular distance. How do you like find that? Is it
How do you
much
compute?
time?
Yeah, that's a really good question. Okay, yeah. So let's say you've got a situation like this. How many of you have ever gone shark fishing or fishing where you stick your poles in the sand? Okay. Yep.
Oh, yeah, right.
All right. So let's say you've got your fishing pole here, and let's say your fishing pole is 2 meters long,
Oh,
like so.
I thought you meant you were fishing in the sand. I was like, that doesn't make sense.
No, you stick your pole in the sand, and we're going to say we've got a fish hanging off it or something like that.
Oh.
Right, blockfish. And it's a 1 kilogram blockfish. The bones are terrible. They're square. Just kidding. And so now we wonder how much torque is being exerted on this guy right here. Let's give it an angle. Let's say it's at a 60-degree angle.
Would you sine theta?
Exactly, yeah. Now this is going to be new and different. When we talk about forces, a force is acting on an object without regard to where it's acting. When we talk about torques, a torque is about a specific point of rotation. So this is an important idea. I will be writing G, won't I? Torque is about a specific point of rotation. And you can measure torque about any point of rotation that you desire, but usually the problem will ask you about a specific point. And in this particular case, we are interested in the torque about point O, our origin, which is the point at which the pole is sticking into the sand. So the question for us is, what is the torque about O? All right. So in order to answer this question, we need to first of all do a free body diagram for ourselves so that we can see the forces acting on it. We are going to pretend that our pole has negligible mass because it's relatively negligible compared to our blockfish. So our free body diagram looks just like this. We have a 10 Newton force pulling down right here. And our free body diagram is going to be a little more complicated because we're going to put in distances and angles. We didn't used to have to do that, but now because torque is force times perpendicular distance, we're going to need to do that. Okay? Now, the torque that's being exerted is being only exerted about the perpendicular component of distance. What you guys just discovered at your table sitting there was that the parallel component of distance does not receive any torque, or if you want to think about it, the parallel component of force does not exert any torque. Only the perpendicular component of force exerts torque. So if I think about the distance right here being split up into a component that is parallel and a component that is perpendicular, then it's going to be force times distance perpendicular that gives me the torque exerted. Well, how do I find that out? It's pretty simple. I've got a nice little right triangle that's formed right here, and I can see that d perpendicular divided by the entire distance is equal to the sine of the angle between these two. What's the value of that angle? 30 degrees, right? And if I solve for d perpendicular by multiplying both sides by d, then I can see that d perpendicular is distance times the sine of the angle between force and distance. And that's 2 meters times the sine of 30 degrees is 0.5, or 1 meter of distance right here.
Is it better to use sine of 30 than cosine of 60?
Yes. Keeps your head straight on some things. Okay? So that we have now the torque is equal to force times distance perpendicular, or 10 newtons, times 1 meter, or 10 newton meters of torque, which is coincidentally the same as what we had for our meter stick. Yes, sir.
So something I still don't understand is that how is the D perpendicular? What is perpendicular?
Ah, it is perpendicular to the force.
So that's like the distance traveled by that force? Or?
Interestingly enough, there is no traveling in our situation yet. So Deja, you do the whole demonstration again. Push straight down on it. See that? As long as I'm pushing back, then there's no distance traveled, but she's still exerting a torque around my shoulder.
Yeah.
So this is not like the computation of work where you had to have a distance traveled in order to get it to work.
So what does the D stand for?
The D stands for the distance from the point of application to the force all the way back to the pivot that we're asking about.
I don't really understand that.
Deja, one more time. So the force is being applied here. The distance is the distance all the way back to the pivot, where the turning wants to occur.
So that's the perpendicular distance.
Exactly so. The force that she was exerting was in this direction. Perpendicular to that is the distance right here.
Right, so what if it was not like perpendicular force?
Yeah, so that's actually what the situation that we have here. We've got this rod, and we have the fish pulling down, and there is a 30-degree angle between the force and the rod. And so to compute the perpendicular distance, we computed that as distance times the sine of the angle between. And that gives you, this is like we call it the moment arm distance, you might call it the leverage distance. It is the perpendicular component of the distance, perpendicular to the force that's being exerted there. Alternatively, we could have taken our force and split it into components, like this, F perpendicular and F parallel, and only the perpendicular component of force exerts any torque. And we would have gotten exactly the same number, because we would have been taking that factor of sine 30 degrees and applying it to the force instead. Does that help?
Yeah, yes, a lot better.
Good, yep. So there's two ways to visualize it. One is force times perpendicular distance. The other is distance times perpendicular force. And both give you the same thing. That was a good question. So let's summarize it all. And that is that the torque is equal to force times perpendicular distance, which is force times distance times the sine of the angle between.
Between the force and
The distance. Now, let me show you where this is of extreme practical value to some of you. Are we ready? Okay. If you are in robotics, then this situation happens all the time. You have some kind of an arm that has a weight on it. And what you want to be able to do with that arm is to flip it, just like that. And the question is, can your motor actually handle that flipping? So let's put some real numbers to it. Let's say this is the crudest example here. We're going to put the motor directly on our arm. Now, we don't usually recommend this. We like to have our motor attached to a gear, which then drives the arm. But for simplicity, we're going to do that. So here's our motor. And our motor is going to be attached to the arm right here. And the arm is now going to have some kind of a weight on it. And let's make up a number for the weight. Let's say that weight is 1/2 of a pound. In robotics, unfortunately, we end up having to work in terms of pounds and inches a whole lot. And then you got to worry about ounces. How many ounces are in a pound? 16. Okay, good. So we have a 1/2 pound weight. We're going to have a 16-inch distance right here. And now what our motor is capable of in a sustained kind of way, the motor can exert a max torque of about 200 ounce-inches. Now, in short spurts, it can do more than that. And the question is whether or not this motor is now going to be able to flip this guy and bring him around. So here's how we do the computation. Notice that the motor is given in terms of the total torque that it can exert and not the total force. And there's a reason for that we'll see in just a minute. Okay. So let's take this arm. We're going to pretend that this arm has no weight to it, which is not perfectly correct, but it's close enough because most of the weight is out here at the very end, that 1/2 pound foot. Yeah?
How would you do it if we did do it this week? If we always do it without signaling going in weights?
Oh, how would you account for the arm as well?
Yeah.
We're actually going to learn how to do that. Yeah.
How hard?
But we'll be okay. We'll be good. All right. So the question is, how much torque is now exerted by this weight here? And so we say that the torque about the point of rotation, which is point O right here, is equal to force times perpendicular distance. The maximum amount of torque is going to occur when the force is exactly perpendicular to that distance. That's going to be when the arm is straight out, because gravity is the force that we're talking about. Gravity pulls straight down, and so perpendicular to that is straight out, right? When the arm is up here, then the perpendicular distance is a whole lot shorter, isn't it? The level arm distance is shorter. When the arm is straight up, the perpendicular distance is actually 0, so it requires 0 torque to get it going when it's straight up. Okay? So, now we put in the numbers. Our force is 1 pound of force. How many ounces is that?
8.
8 ounces, that's right. And we have 16 inches of distance. And so now when I multiply these, I get, what's 8 times 16? 128, that's right. 128 ounce-inches of torque. Can the motor handle this? Yes, its limit is 200. It can handle 128. Will it handle it well? Well, as it turns out, it's not going to handle it very well, and here's why. When the arm is fully extended, that motor is going to have to work pretty hard to get it going, so it's going to go slow. Now, as it goes up, the moment arm distance is reduced, and the amount of torque required is much less, what's that motor going to do? It's going to do this. Like that. And so your arm is going to move very unevenly for the simple reason that if you put a constant torque on it, the arm is going to require much more torque to accelerate out here than it does up here. Everybody understand what I'm talking about? So what we need to do if we want to make this a nice, smooth robotic arm is really to use some kind of gearing system to reduce the speed with which it travels and really reduce the amount of torque that is needed for the motor to do its job. And we'll actually talk about gears, but not today. I'm excited to teach you guys how gears work. How many of you know how a gearbox works, basically? A couple of you. Cool. Good. All right, the other question then is, what if you have multiple forces acting on something? So this is the kind of situation that occurs sometimes. You've got a pivot point A right here. Yeah, this works pretty well. You've got a pivot point A right here. And let's go back to our metric system and make this 0.3 meters. And we'll make this 0.1 meter, just like so. And let's have a 200 Newton force pulling down here, and a 400 Newton force pulling down there. And now what we'd like to do is to compute the net torque about point A. Notice once again we're being specific about the point of application, the point of rotation, so that we need to be careful in terms of paying attention to distances. We're going to compute it like this. We're going to compute the sum of torques about point A, and we're going to notate it just like so. And we're going to compute force times distance for each one of the forces involved. So we have 200 newtons times the distance from 200 newtons back to A. What is that distance? 0.3 meters. So notice how we compute, notice how we're visualizing this. We go from the point of application of the force all the way back to its pivot. And we're also going to pay close attention to sign. And our sign convention is that any force that rotates me counterclockwise is a positive, exerts a positive torque. Any force that rotates me clockwise exerts a negative torque. So I take a look at point A, and I visualize this 200 Newton force. If it operates, is it going to have a tendency to rotate clockwise or counterclockwise? Clockwise, just like that. Can everybody see that? The 200 Newton force is pushing down like so, so it's going to push this arm in a clockwise rotation. That means that we're going to count the torque here exerted by the 200 Newton force as a negative torque. Not because 200 points down, but because it rotates clockwise around A. Does everybody see how I'm getting the signs? That's confusing to people sometimes. Meanwhile, the 400 Newton force is also exerting a torque, and that torque is computed by its force times its distance, which is 0.1 meters here. And to get the sign of that torque, we ask again, clockwise or counterclockwise. So we go to point A, and we imagine the 400 Newton force causing a rotation, and if it rotates, it will rotate this way, which is counterclockwise around A. That's a positive torque, positive rotation. Notice that the 200 Newton force and the 400 Newton force both point down, but the 200 Newton causes a clockwise rotation around A, the 400 a counterclockwise. Therefore, the torques exerted by them have opposite signs. Is that making sense to people? Okay. Now we add them all up. 200 times 0.3 is
60.
Yep. 400 times 0.1 is 40, for a net of negative 20 Newton meters worth of torque. These two forces fight each other in terms of rotation around A, and the 200 Newton force wins net because it is at a further distance. Its total torque, 200 times 0.3, outmatches the 400 times 0.1. Yes.
So, like, how did you know that the 200 Newton force would make it go clockwise? Like, what if you were unsure which one would prevail and then make it go clockwise?
Yeah. So it actually is not about which one prevails. It's just about the 200 Newton force. So block this guy out of your mind for a second. And focus just on the pivot point right here. Let that force have its action. If it does, which way does this arm rotate? That's clockwise. So you visualize it. Does your force cause you to do this, which is counterclockwise? Or does it cause you to do this, which is clockwise? If it's swinging in the opposite direction of the clock, positive. If it's swinging in the direction of the clock, negative. Did I do that backwards?
Right.
Well,
You
you did it right for you, back
I did it right for me. Yep. So it's swinging in the same direction as the clock. And it's like that, then that's negative. And if it's swinging opposite, then it's positive. Stage left, stage right.
Counterclockwise to the opposite counter, the way the clock goes. That's what I thought you were saying.
Okay.